I will start us off. Hey, everybody. We are the Seaweed to Bioenergy Group. And so we started out with kind of the prompt of we have this very interesting biological material that seems like people aren't doing very much with it yet, seaweed, and investigated the various pathways for turning it into something useful for the world. So next slide, please, John. So before we talk about seaweed, let's first talk about biofuels because it's not actually as obvious as it sounds. Like your biofuels, sorry. So first, transportation is like 28% of global emissions, and I think everybody's preferred approach is to decarbonization is electrification, but that is still going quite slowly. Only like 2% of new cars in the US are battery electric vehicles. So one route we can take is to replace fossil fuels with renewable biofuels. And biofuels can have dramatically lower net emissions because they are made from plants, which take carbon from the atmosphere to like grow themselves. And then when you convert that mass into fuels and burn it, it just returns it to the atmosphere. And so you're not doing the bad thing with fossil fuels where you take carbon that has been underground for millions of years and pump it into the atmosphere. So you should have a close to net zero effect on actual like CO2 levels in the atmosphere. So the downside of this, many attempts have been made to make economically viable climate-friendly biofuels, and they have not been very successful. Spent probably billions of dollars on microalgae-based fuels. The most common one in the US today is corn ethanol, and that's largely because of something called the Renewable Fuel Standard that requires a certain amount of renewable like biofuels to be mixed into various transportation fuels. But corn is kind of an ecological disaster. It has a lot of bad things going on for it. So where does that leave us? If we're still interested in biofuels, we kind of need to try something different. And so I would say enter seaweed. Seaweed has a number of advantages as an energy crop. It grows very fast, one of the fastest growing like organisms on the planet. You don't have to water it or fertilize it. It doesn't compete with food or other things that we want to use land for. And it grows in the ocean, which is like 70 some percent of the planet's surface area. So there is massive potential scale. The biggest issue is that it is not yet being grown at scale. And there's many reasons for that. It's very difficult to permit and like to even get permission to grow seaweed. There's all kinds of problems, but we have kind of chosen to wave that away and not worry about it too much. But next slide, please, John. One thing I'll say is that there is a certain type of seaweed called Sargassum that is an interesting place to start. It is currently a waste product in the Caribbean. So there's enormous blooms of Sargassum on the order of like 20 megatons a year of Sargassum that are growing in places where they did not historically grow. This started about 10 years ago. And it's thought to be from nutrient runoff from the Amazon, the Mississippi, and Western Africa, causing these big blooms. They show up on the beaches in the Caribbean, and it's a huge economic and like nature problem because when it dies, it it decomposes, it releases noxious gases, it kills the wildlife, it does all kinds of bad things. So if you can take that from being something that is causing a negative impact on the world and use it to make biofuels, that could be a really interesting net benefit. So I'll hand over to Noah.
Got it. So the good news is there are several ways to turn seaweed into bioenergy. There's some bad news too, but we'll get to it. And what you see on screen is a high-level map of some of the processes that take seaweed from a plant to an energy product. And up front are some generic steps, and then there's some kind of more specific steps that generate energy, such as fermentation producing ethanol or pyrolysis producing a number of different end products. And what we did is we looked at the entire map and then selected some of the end products, the ones in gray on the right, and then kind of dug in to the extent you can in a few weeks into their processes and into their markets. And I worked on ethanol, for example. And so we kind of generally found that these are largely technically viable and well understood processes with relatively poor economics compared to existing energy sources. This kind of, I mean, I don't want to completely generalize because, you know, we have some ideas that I think are a bit more promising, but that was kind of a broad theme. So these are things that can be done. People know how to do them. There's good research on it. But when you make the end product, the economics aren't great. For example, seaweed ethanol is not price competitive with corn ethanol. It's right now not even close. Although if oil prices were higher and gas prices were higher, or if we had kind of big regulatory intervention like carbon pricing, the viability of the energy products would change quite a bit. So you can kind of just, you know, as a snapshot, here's kind of end to end how it would work. And, you know, you can see the ones we looked into. And then I'll let Cass dig into some of the more specific processing approaches as well.
Yeah, thanks, Noah. Yeah, so basically these are all the boxes that were in red on the previous slide, and it's a little technical chemistry wise, but if you're interested in the technicals, there's a great class from Penn State University that talks about all this that we can link to. But basically all these different methods, the ones where you burn things, they just vary kind of on temperature or pressure or whether there's oxygen or not. And just by varying those parameters, you change the composition of the end products, like how much gas you get versus how much liquid you get versus how much char you get. And yeah, so you can change all those levers and change the end composition. And the interesting thing that we found was that like all those end products, there are other chemical processes that you can use to convert between them. So if you end up with gas, but you want liquid, then you can use like Fischer-Tropsch to like turn it into liquid. And if you have liquid, you want to turn it into gas, you can do that as well. So they're all pretty interchangeable. Obviously, there's like a energetic and financial cost to do those conversions. And then the other thing I want to flag is when we say these things are not economically viable, it's not that bad. Like none of these things have been done at scale, but like for on the papers that we've read, and you can find these papers too by searching the fun phrase techno-economic analysis. If you like search Google Scholar with that, like you'll like scientists have done the calculations for how economically feasible each of these chemical processes are. But yeah, they might just be off by like $1 or $2 per gallon. So it's something that like a subsidy could cover. Yeah, so we primarily focused on hydrothermal liquefaction and anaerobic digestion out of those red boxes, because looking at this chart, we're since we are working with seaweed, we're interested in using the entire biomass, and ideally we wouldn't have to dry it because seaweed has a lot of water, so we wouldn't want to dry it before processing. So yeah, hydrothermal liquefaction really jumps out here, like being good against along those dimensions. And yeah, liquids are just a lot easier to deal with than gases as well, which you would have to have expensive containers for, although I guess the liquids are very corrosive. So difficult problems all around. Yeah, so I will pass it back to Tim to talk about hydrothermal liquefaction.
Great. So yeah, as Cass mentioned, there's a bunch of these different pathways. The one I am personally most excited about is this one called hydrothermal liquefaction. I like it because it is very conceptually simple. It is literally biomass, water, heat, and pressure, and you get an oil, mostly a bio oil, and there's also like a sort of water with dissolved nutrients as another output, and then a small amount of solids that are basically biochar. But that bio oil can be upgraded relatively easily and then refined further into like various types of fuels. So you can think of it as kind of a drop-in replacement for crude oil. And since crude oil is the starting point for basically our entire like petrochemical economy, that's pretty interesting to be able to swap it out with something totally different. Other benefits, I think Cass mentioned this, but you don't have to dry the material. It handles wet material. So the only like at scale production use of hydrothermal liquefaction in the US right now is It's being tested out at a few different wastewater treatment plants for basically like processing human waste and turning that into fuel. And it works. The other benefit is super fast. So it's like 30 minutes in the reactor under the heat and pressure rather than having to wait like weeks for biological processes. I'm not sure who's next.
Oh yeah, so we put together all our findings into a lean canvas business model, and yeah, we can link this afterwards, and probably don't have time to go into it, but just to call out a few interesting things. We spoke a bit about how the economics are difficult, and a researcher we talked to said it's especially a problem because fuel is cheaper than bottled water in most places. So that's when that's your output, that's a little unfortunate. So his main recommendation was targeting areas that are a bit off the grid, because then when you try to ship conventional fuels over, then the price increases. So if you can generate biofuels locally, it might be a little bit more price competitive. So yeah, that was interesting. Next slide. Yeah, and then we also have some personal reflections from this experience. We've read a lot of scientific papers, and that might have it was very painful, and might have not been the best way to go about things. Yeah, we really admire the groups that just went out and talked to people. And if we were to do it again, we would probably do it that way. The other thing that was interesting was byproducts from these processes are cool. So for instance, like with bioethanol production, you can generate a sugar called alginate, and you can sell that too. But then you have to like invest extra into capex for building the equipment to do that. And sometimes that, like having that extra capex investment makes it actually like once you time discount the cash flows backwards, it's not actually economically a good idea anymore. And so we've seen that. But yeah, we really need policy changes and subsidies in order to build this market. But there's a lot of hope and there is a lot of momentum. We are in the second wave of biofuels, and our teammate Duncan, who couldn't be here, mentioned that Green Wave, which is an organization that supports seaweed farmers, received thousands of applications. Like thousands of people want to be seaweed farmers, and they only have the capacity to on-ramp like 100 of them. So there's a lot of demand for this stuff.